So, friends, welcome to this lecture series, and today we will going to discuss about this classification of mass wasting part 2. So, if you remember in the last class we are talking something about this classification and we confine ourselves in the hill slope. So, we classified the creep, the slowest movement, the solifluxion, the gelifluxion, and we found for the solifluxion and gelifluxion there should be a criteria that this base of the system should be water impermeable and water should not escape from the system so that movement can continue. Now, we will confine ourselves within the valleys itself. So, in solifluxion or gelifluxion and in creeps, it is along the slope, a hill slope is there, along the slope the movement is there like spreading somewhere. But those classification now we are going to discuss that will confined within the valley. So, this is start with the debris flow, earth flow and mud flow. These three terms are applied to the types of mass wasting very similar to solifluxion. However, they commonly flow along the valleys itself, whereas sheets on solifluxion and gelifluxion they are looking like lobes and spread entire hillside. But here once we say debris flow, earth flow and mud flow, that means here a valley is associated. All those flow material they are flowing along the valley itself, not along the hill slope or hill slides. The very important point here to remember is that the distinction is that the debris flow, earth flow and mud flow, gravity act directly on particles that drag along interstitial fluids rather than on a fluid that entertain the particle. So, here gravity is directly affecting with the associated particles, associated crust. So, it is dragging down. So, that means with the help of this gravity the whole system is flowing along this valley, and when this valley is opening up the system getting slower and slower and it will spread like somewhere. So, whenever this confinement within this valley it will continue, this mass will continue. Here if you see these figures are indicating here this side is the wet condition and this is dry condition. Here slow speed and here fast speed. We have mud flows, we have debris flows, we have earth flows. Here we are confining at the top part of the system. That means in the as far as the earth flow is concerned, it is relatively slower. But this wet condition is compared, the mud flow and the earth flow both are they both containing sufficient amount of water, but in debris flow the water content is relatively less. Flows almost always result from excessive rainfall and oversaturation seems to be the major factor of their formation. Oversaturated materials, that means water content is more, so that it can flow. To sustain its flow, water should not escape from the system. Okay. But very important thing that it is differentiated based on the valleys, the confinement within that valley. One particular type of flow, it is called lahar, it is an Indonesian term. It is this flow, particularly this terminology, it is confined for the volcanic material like the tephras, the lapillis, the volcanic ash. Along these volcanoes or the side of this volcano, these materials are gathered. By some means, if water is associated with that, this material will flow along these valleys and this is called lahars. It may be hot and cold. So, it is an Indonesian word that describes debris flow at the flank of this volcano. This is triggered by pyroclastic eruptions, saturated and sustained tephra or the slopes of this composite cones. So, this material will move down, this terminology layer is used here. Other sources of mobilizing water is bridged craters, melted snow and slide dammed river. Layers may be hot and cold. The water content is comparable to that of the wet concrete. Whenever we go for concrete works for our construction purpose, whatever the water is there, this water content of layer can be compared with that. So, that means the system is flowing. Essentially, it is consisting of volcanic material, volcanic ejectas. Then another mass wasting term, it is called spread. Spread means it is spreading. So, spreading on lower slope material, lower slopes. So, what is this spread means? Suppose we have a different alternative layers of, suppose for example, the upper layer is consisting of sandstone and the lower layer is clay. By some means, either it is earthquake or by some means this system is totally sagged. So, in the clays there will be liquefaction. So, liquefaction there will be turbulence within these clay bodies. So, once there will be liquefaction, the system tends to flow, the upper layer remain intact, it is coherent, it is total cohesive strength is there. But once this lower layer wants to flow, there are cracks will develop in the upper surface, and through these cracks those materials they will try to break into blocks and will fall within that lower layer and will be separated out. This type of movement, it is called spread. That means the system is spreading. So, by definition, a spread is defined as the lateral extension of cohesive rock or soil mass combined with general subsidence of the fractured cohesive material into a softer substrate. Here softer substrate, it is the clay as we are discussing, and this cohesive material is the sandstone. The cause is usually liquefaction of the substrate while the surface remain cohesive strength. So, as we have discussed, the clay, it is liquefaction will be there, and the sandstone above this clay, it will remain cohesive. Rock spreads are typically extremely slow, as when brittle layers are rafted along by slow deformation of underlying ductile layers or ductile materials. Spreads are common form of landslide in low gradient slopes, low gradient terrains. During earthquake, when rapid shaking liquefies the sediment below the water table and displaces overlying rocks in the drier material. So, if we have this liquefaction occurs below the water table, the whole material try to move off. So, that it creates crack on the upper layers, the intact layers, and these blocks that tries to move different directions, and that is called the spreads. And it is most common in low slope areas like the plains. Then another type of mass wasting, it is called slide, where a mass of rock or weather debris moves downhill along the discrete shear surface, that is a plane, a definite plane is associated. On a definite plane, if rock mass may slide, debris may slide, anything may slide on this surface. So, this defined surface is there. So, based on the defined surface, that is why it is called slide, it is sliding down. Slides are subdivided into either rotational or it is translational. So, rotational slide, that means here this plane, it is a curved plane, the plane of failure, it is a curved plane. So, that material rotates, or it is translational if it is a planar surface. Here if you see in this figure, this plane of failure, if you see, it is a curved plane, it is, that means any material which will detach from here, that will try to move like this. So, this is rotational slide. Here in this particular figure, if you see, here this plane of failure, it is straight, it is a plane. So, this material or this block which detached from the main body, it will slide down here. So, this is translational side, this is rotational slide, and in the irrespective of translational or rotational, a definite plane is defined. On this plane the motion is going on. So, that is slide. Subcategories of the slide in various classifications are there, that is include slump, rock slide, block glide, mud slide, debris slide and debris avalanches. So, here some figures are given. This figure denote to slump, slumping of material here, then debris avalanches, avalanches very rapid movement of avalanches, then debris slide, it is sliding down, then rock glide, this rock intact rock, if you see here this whole rock as a whole block, it is gliding down, it is block glide, then mud slide, mud is sliding down. So, depending upon this material involved, depending upon this nature of this plane of failure, this has been classified. First is the slump, is the form of slide most common in thick homogeneous cohesive sediments. That has to be clarified here. It should be in homogeneous and cohesive sediments. The surface of failure beneath a slump block is spoon shaped, concave upward or outward. If you see in this figure, this is the plane of failure, it is concave upward, it is like spoon shaped. So, once the material is sliding from here, detached from here, it has to undergo a rotational motion, and here it is concave upward, and this side if you see here, this is convex upward. See, the upper surface of a slump block commonly is tilted backward because the entire mass rotates at the lower part, moves upward and the downhill. So, here it is rotating. So, rotational motion is involved in the slump, and this it is a homogeneous material and cohesive material. Vegetation or even houses may be carried intact with the surface of failure, the large slump block. Swamps are tens of thousands of meter wide and may be single block or consist of multiple slides. Sometimes ponds are generated here. For example, if you see in this figure, here these different blocks, this is one block, this is another block, the blocks are detached gradually and is moving rotational motion, and here if you see a pond is developed. Pond plays major role in motion or this sustained motion of this slump block. For example, suppose ponds is filled with water, and once the system moves, that means there are cracks are developed, weak planes are developed. Through the weak planes, the water will percolate down. Once the water percolates down, it behaves as a lubricant, so that this rotational motion, this detachment, that will continue for long time. If ponds are not there, if water percolation is not there, it may discontinuous motion will be there, that means to certain extent it will move and it will rest. But once the water is percolating down and it is increasing the weight of this body, it is also behaving as a lubricant, so that motion will continue for long time. So, water plays major role here. Slumps may be caused by water erosion undercutting the foot of the slope. For example, if this figure, if you want try to understand here, suppose for example, here this is the cliff surface and this is the water body, and with constant erosion, constant heating of this water, here you see there will be erosion of this rock body, and once this erosion takes place, this part of this block this become unstable. So, that means due to this instability, this part of this rock gradually sliding down on a curved surface, this is called slump. So, that means they are sometimes mitigated by loading the base, that means for the engineering remedies. If we are loading the base here, we can mitigate to certain extent. So, loading the base with rubbles or the gabion walls, so that this water will only escape, but the material will be supported. For example, here the faulty engineering structure, suppose here we are removing the material. So, that means we are creating a cliff which can free fall here, which can slump down. So, in that case what we generally do here, we are creating the gabions, the walls composed of boulders, it is tied with nets, with metal nets. If you see here, this metal or plastics or some types of polymer is there, these nets. So, that means we are allowing the water to percolate, water is removed, but it is supplying a support to the rock mass there. So, that is why by loading the toy with suitable material, with suitable design, to certain extent we can prevent this type of slump motion. So, there also a common result of faulty engineering design of called embankment. So, whenever you go for road alignment along the hilly terrains, it is tunnel alignment along the hilly terrains, we must be keep in our mind that once we dress a slope, we redesign a slope, it should be stabilized with proper support, so that there will be no slumping, there will be no mass wasting from the slope to the road. So, due to this faulty engineering design, there are crores of rupees we are spending in the hilly terrains to stabilize the slopes, which are naturally caught earlier. The most diagnostic feature of an ancient slump area is the hummocky or chaotic landforms on it. It is very important to see here. This diagnostic characteristics of ancient slumps. Ancient slump has to be understood properly to go for proper engineering design. Otherwise, suppose for example, in an area we are assigned for engineering development for road alignment or so, we do not recognize the ancient slumps. So, ancient slump may be reactivated with time. So, that is why once we identify this is the ancient slump. So, that means we have to go for remedies, proper engineering remedies we have to go. So, until unless this slump will again reactivated during this time, and finally, it will block our developmental program. So, how it will distinguish? So, generally this ancient slumps, they are distinguished by hummocky and chaotic landforms. Hummocky landforms, hummocky structure you might be knowing. Hummocky, that means it is concave and convex type of material, this is hummocky structure. Then chaotic landforms, there is no arrangement of landform arrangement. Some lobes is here, some lobes are there, something like this. So, it is chaotic arrangement of landforms, and this hummocky structure in the ancient slumps can be distinguished. Unless the material removed as a single slump block or it is thoroughly fluidized as a mud flow, the surface mass is broken rock rubbles and mounds or pits, sometimes the systematic transverse ridges or lobes, but often totally unsystematic. So, these are the signature how you will identify these ancient slopes or ancient slumps. The debris is poorly sorted and can easily be mistaken for glacial tilts also. This is important. In hilly terrains, in geological past, we have many glaciation and deglaciation events. So, these are suppose in the hilly terrain it is lying there. So, if we are not able to properly identify this slump material, we can easily mistake it for the earlier moraines. So, that means proper understanding, proper identification is must for proper engineering remedies. Here the surface topography of slump blocks can be easily mistaken with lateral moraines. For example, if you see here, these are this debris material is being mined here, and this is nothing, it is this slump material, ancient slump material, but it should not be mistaken for ancient moraines. Okay. But their characteristics will be same. Moraines, it is totally unsorted material will be there. Similarly, slump rocks, it is totally unsorted material will be there, but there should be a geologist should properly distinguish what he is dealing with. Okay. So, if ancient slump material is there, it is mistaken by moraine. So, you will not take proper engineering remedies. So, that means your again engineering design will be faulty. So, that is why proper identification is must. Then another classification of the slide is called mud slide. Depending upon the slope gradient, degree of saturation and grain size of sediment emerging from the toe of the slump, it can be called mud flow or mud slide. A mud slide moves over or between discrete shear surfaces in a lobate shape, somewhat slower than a more turbulent mud flow. At its terminus, it may form a bulbous lobe. For example, if you see this, these are the lobes, these are the mud floors or mud slides. So, mud slide, that means there will be turbulence, motion will be there, discrete planes will be there, within that planes there will be motion. So, those planes, they are the sliding planes. Then rock slide or block glide, the simplest form of translational motion is the rock slide or block glide. The movement is relatively rapid and the most common occur where steeply dipping strata or sittings nearly parallel to the surface slope. It is very important to hear. This is the fastest motion. Suppose a plane is there, discrete plane is there, and the rock mass are fractured into different independent blocks. On this block, on this plane, these rocks can move violently. Suddenly, this rock can transfer down. So, this is called rock slide and block glide. That means, the whole block, intact block is gliding down. This is a glider, this is a gliding plane. Okay. So, in this figure, if you see, these are these rock slides, and here the rock sliding is there. This is the block glide, the block glides are there. So, along this plane, this rock material is going down. Rock slides are generally shallow. A heavy rain or freezing and thawing provides fluid pressure or vibration breaks of obstructions and reduces the coefficient of friction of this glide plane, and detached material comes down. So, these are these few regions, either vibration will be there, saturation will be there, heavy freezing and thawing will be there. So, that this rocks try to move along this discrete plane. It may be shatter at this down slope. Suppose it is heavily, it is coming down and it is hitting to this lower slope material. So, it may be shattered there, or depending upon this hardness, depending upon the physical property, it will be shattered or will remain intact, it will depend on that. Rock slides or block glides have no specific size. So, block may be of this much size, or may be this much size, or is may be of this much size. So, there is no specific size is there, but thickness is normally only about 10% of their downslope length. That is important to note it there, but thickness is here, it is less than 10% or about 10% of their downslope length. This is rock slide. Deep of strata, spacing and orientation of joints and other discontinuities in the rock mass that affect the rock slide. If rock strata dips less than that of the hill slope, so individual slabs are unsupported at the downhill edge and are more subject to slide. If the dip is more than the dip is more, it is steeply dipping than the hill slide, it may fail and locking out towards the toppling. So, now if you see in this figure, here this is the over dip slopes and it is the deep slope and it is other deep slope. Here the slope face is there and deep is there. Here rotational failure, because the failure will be like this, here the failure will be like this, it is rotational failure will be there. Here simple sliding will be there, here simply sliding will be there, but if these joints are vertical, then topples are there. Similarly, here it is shell and sandstone. Now, you see this system, it is toppling, that means rotational motion will be there. So, depending upon the deep and slope, deep is in the rock body, slope in the rock surface. So, slope and depth relationship that describes or that defines what type of motion will be there. Rock slides can be deadly if large mass slide down along the sloping joints of a bedding surface. Such a plane of weakness was involved in the Vainot Reservoir disaster in October 1963 in North Italy, where rock slide, suppose for example, if you see in this figure here, suppose is the lake and reservoir and this is the plane of weakness. So, if this material is sliding down to the reservoir, it is creating huge waves and the energy of that wave may be sufficient to breach the dam axis. So, here if you see this rock material, if it is sliding down, huge rock material is sliding down to the reservoir, that this dam may overflow and the overflowing of dam, it will cause damage to the dam itself along the downhill sides or dam sides. Then avalanches and debris slide. Any large catastrophic landslide may be called avalanches. That may be ice, the rock material, that may be mixture of that, anything, the large and catastrophic landslide, that is called avalanches. Then they can include the broken rock, that may include the ice, that is slow and usually the mixture of all those material, that is called avalanches, and suddenly it is coming down. The obvious general cause for humid climate debris avalanches is saturation by heavy rain. It is very important. In humid climate generally there are heavy rains occurs. So, in heavy rains once the system is saturated, so in saturated condition the whole material is coming down. So, this is called avalanches within a time, within a very fraction of time. Summer storms are known to fluctuate many folds intensely, even over the time span of hours or less. During the brief interval of this heaviest precipitation, water alone may be ultimate cause of this failure. So, if it is heavy rain is there, some fracture planes are there in the rocks and these rocks through the fracture plane, once this water percolates down, it behaves as a lubricant. So, it accelerates the motion. See the whole hill slide, it is coming down with the homes, with whatever these structures are there, with the trees and everything, it is total system is coming down, that is called avalanche. Lightning striking trees in vibrating thunders and the tree fall down, so this is called also avalanches. So, that means there are different mechanisms, either it is lightning, it is vibration, it is heavy rain, it is earthquake, in reality everything, if the whole system is coming down suddenly, it is defined as the avalanches. So, very large terrestrial debris slides and avalanches have received renewed interest in recent years because shape and size of their deposits and their probable mode of origin are similar to those of debris slopes below the crater walls, cliffs of Mars and Moon. That is very important to see. In Mars, in moons, whatever the photographs are coming, we are looking the similar type of mass flow as the avalanches, debris avalanches, as we are looking at the earth. So, it is believed that these systems which is working on the earth surface, probably this same system was working in this Mars and Moon surface in geological past. So, that is why interest is being grown on this to understand what is exact mechanism behind these debris avalanches, so that we can understand the lunar and the Martial processes. In large debris side, the ratio of vertical drop to horizontal runout distance is very small, equal to tangents of angle ranging from 3 to 7 degree. These angles are typically 1/10 or less than the angle of mass friction of the rock debris. So, if you remember our earlier class when we started about this mass wasting, we are talking something about the strength, this angle of repose or so. So, here the large debris side, the ratio of vertical drop to horizontal runout, the distance are very small, equal to the tangents of angle to 3 to 7 degree, and these 3 to 7 degree are typically 1/10 or less than the angle of mass friction of this rock debris. So, that means the angle of repose is more than the angle of repose. So, that is why the system is going down and its horizontal distance is less, is restricted. Then another type of mass wasting, it is called fall. It is free fall, that means only the air resistance will be there. So, to prerequisite this for the fall, this there should be a steep slope and there should be weathered rock material, there will be jointed rock material. So, that this material which is detaching from this rock body, it is freely falling on the surface, freely falling to this valley, and air resistance is the only resistance, nothing else. So, fall is a distinct category of mass wasting, but it is rarely independent of subsequent events like earthquakes and others. So, that means we need a triggering event, a triggering mechanism, so that the whole system should shake and the block should be detached from this main body. And if you see these two figures here, due to these are the joints, or the exfoliation joints or this pressure release joints to this free body, free part of this valley, and this is the potential rock that can fall. And in this figure, if you see, the system total is falling down. So, here the massive rock is falling down, only the air is in. You see, it is not in contact with the main body. When it is falling down, it is not contact with the main body, it is free fall, only air resistance is there. Then whenever we are talking something landslide, we should keep in our mind that landslide does not occur on this subaerial system only. There are landslides that has been reported in the submarine system also, submarine landslides. Nowadays in the present day ocean, we experience submarine landslides. In the past oceans, in geological past, when there are ocean was existing in certain parts, there also some submarine landslides had been reported, and those submarine landslides or the past submarine landslides, they are now recorded within our rock stratigraphy, within the stratigraphic record. So, by identifying those submarine landslides, we have to precisely identify those rock structures which are nowadays occurring with the present day landslide. So, that we can correlate, yes, those rock structures which are preserved in the stratigraphic section, it is indicating a particular submarine landslide. So, the term landslide is restricted neither to this event of land nor to the specific process of sliding. So, anywhere either in the submarine or in the land surface, if the sliding is going down, if the rock mass is going down, so that is called landslide, a submarine landslide. You might have heard about this turbidity current, Boma sequence, like that. For turbidity current, they are these characteristics features or characteristics events of the submarine landslides. And this turbidity current, if you see here, there are debris flow and there will be turbidity current, and finally, this will turbidite deposit will be there. Here we will get this Boma sequence like that, whatever the studied you will be taught in sedimentology or so. So, these type of deposits, if we are finding in our present day rock record, that means we can say these are the deposition or they are the outcome of these ancient submarine landslides. So, here some of these photographs I have taken for you. It is the submarine landslide recorded in a stratigraphic record in Proterozoic sea. It is from this Pranita Godavari valley. It is a Proterozoic age. If you see here, these are the autoclastic limestone flows. Here, these are the limestone clasts. These are the limestone clasts, and the matrix is also limestone. It is autoclastic. Autoclastic means same clast, same matrix. It was subsiding at the same place where it was deposited. So, those mass flows in this ancient Pranita Godavari valley, they are indicating the landslides, the submarine landslide in the geological past. So, this is the end of the story. So, landslide we can summarize here. It is should not, this terminology should not confine within the land itself. So, there are marine events, there are some events occurs in the marine, there is failure of material which is also termed as landslides, and landslides depending upon this material involved, depending upon this site, depending upon the velocity or the speed of movement. So, depending upon the slope, they are classified into different categories. So, two main thing is that material has to flow with the influence of gravity, either it is on the hill slope or it is confined in the valley. So, depending upon those circumstances, depending upon those parameters, the landslides are named, and different landslide has to be classified or classified into different categories for our proper understanding. And if we categorize it, so that means we can design our engineering structures depending upon that. We can take some engineering remedies depending upon the probability of what type of landslide is going is expected in particular area. So, this much is for today. We will meet in the next class. Thank you.